Congratulations, Yuri. I think I was a professor at the University of Illinois at Urbana-Champaign for 10 years, and that's where we met a few times. You, of course, didn't come to visit me, but you visited Urbana-Champaign often for personal reasons. And he gave a talk, I remember, on quantum computing back in the day. He also, I remember at the dinner, as my wife always tells a story, that we were having dinner and you were explaining something, and then you said something, oh, you can Google that. Then you corrected yourself quickly, oh, you can Bing it. So I met Yuri a few years back. I think I'm a mathematical logician. This will be a little bit more on the logic side. I will try to bridge, as Yuri, this connection to or the bridge towards theoretical computer science. In general, what I'm doing is I'm really interested in, and hope this kind of goes back to what Yuri has done. I think on Wikipedia, so this says his period in Israel. Really classical results in questions in decidability of certain logical or mathematical structures. Just to give you my kind of overview, I mean, very brief explanation of what I'm trying to do is, of course, we all know that Pressburger showed that the theory of the natural numbers with plus is decidable, and Gödel showed that with multiplication, the theory becomes undecidable. For me, that always rises to a natural question or a natural program in logic. That is a study of expansions of the natural of Pressburger by fragments of multiplication. This is a really old research program. Maybe the first result in that direction is due to Putnam, and that is if you add to Pressburger the set of squares, and this becomes undecidable. That's really, I mean, that is not a hard theorem, and if you're bored by my talk, and you can really just think about solving this problem, and it's not so hard with the binomial formula. Yes, sorry. In some respect, I mean, whatever you want. So kind of the whole part of the whole of the results is always is that even if you add very, very little, like just the squares, set of squares, then you get undecidable. So it's really kind of minimal things you can possibly add. So the fragments will be very, very small. And usually in this example, this will really be predicates. Yes, that's why. Yes, that's why it's undecidable. So kind of you add, even if you kind of add a little bit and hope to be staying small, it's a hard question how to then show that it stays decidable. I want to point this out. I will not talk too much about this. It's, of course, I find this also very interesting in the question if you do it over the real numbers, because then you have a little bit of more, let's say, space to work with. For example, you could add scalar multiplication by irrationals and stuff like this. But today I will really stay mostly over the naturals. So this is really my my motivation for as a mathematical logician. But there's a really close connection to theoretical computer science. Okay, try to move this. Yeah. So this is Cobham's theorem. So Cobham's theorem basically says if you have two multiplicatively independent integers, and this is a foundational theorem of theoretical computer science, and their x is both k recognizable and l recognizable, then it has to be very simple. And so it has to be very simple. I mean, just ultimately periodic. For those of you who don't know, but probably in this audience everyone knows, if you want to put this, set x is k recognizable, basically if the language consisting of the base k representations is accepted by a finite automaton. So really, this is a way of coming from words to actual sets. This is how I will interpret this, and of course. Then examples are, for example, k to the n. This is given by this finite automata, or slightly more interesting, but the main example I will consider today will be k to the n is, for example, the two Moore set. which is the set of natural numbers where the digit sum is even. That is given by this automata. Okay, Cobham's theorem, of course, generalized also to higher dimensional sets. So if you take a subset of n to the n and say, okay, recognizable if there is a language consisting of the base k representation of these elements, if this is recognized by a finite automata, you have to be a little bit careful to make this precise. But let's not worry about this. And Semenov showed also in the late 70s that if they're multiplicatively independent, K and L, and you have a set, then this K and L recognizes if and only if it's semi-linear. So very simple. For us and for me, it's always definable in Pressburger arithmetic. Of course, you don't have just ultimately periodic sets. You have to be a little bit careful in higher dimensions. So now to come up the maybe I read Yuri's paper on a survey paper on monadic second order theories, and there he also explains a little bit how he kind of became interested in second order monadic theory. And for me, maybe it's very similar because I really I looked at these structures, I looked at the natural questions like defining or kind of deciding fragments of multiplication, and it becomes very quickly, you have to look at structures that are basically bi-interpretable or with monadic second order theories. And one of them is Büchi arithmetic, where you take the Pressburger arithmetic and you add this, I would call it valuation function, that maps a given natural number to the largest power of k, dividing it. Basically, if you add this to Pressburger, this allows you to talk about k-area representations definably. That's really what it means. And Büchi in his paper on the weak monadic second order theory of one successor, it essentially already showed this, that a set is k recognizable if and only if it is definable in this expansion of Pressburger by this VK predicate, and the theory is decidable. So in particular, if you take any k recognizable set and you put it on the natural numbers, then it remains decidable. Okay, so there this stands. And then the question I'm interested in is if you take is this connection to Cobham's theorem in a moment. And I want to put it like this. So for me, restated Cobham-Semenov means that a set is definable both in this Büchi arithmetics for different k and l, if and only if it is Pressburger definable. So I will yes. Sorry, I should have said this. For now, because it mostly is first order definable, it will be first order definable. When it is second order definable, I will explicitly say so. Right, and so for me, the question I found this very interesting is so by Cobham-Semenov, you know that if you have if you have a k recognizable set and it's not simple, i.e. not definable in Pressburger arithmetic, then it cannot be L recognizable. But assume you take two sets, X and Y. X is K recognizable, but not Pressburger definable, and Y is L recognizable and not Pressburger definable. Then you can ask, okay, what if you have these two operators coming from different numbers K and L? What can you say about the decidable of this theory? And the result I want to talk a little bit about today is that if you put them together, then the theory becomes indecidable. So not only are K and L recognizable sets different, they're computationally as orthogonal as they can be. So this is just restated. Yes. Yes, please. With equality. Yes.
How important is it to have how much different?
Interesting, yeah. I will say a little bit about kind of the edge cases. I'm not sure I have a good answer for the equality question. So what I also want to point out is this is the Cobham-Semenov is immediate corollary of this result, because if you take a set that is the X that is the both definable in Büchi over K or VK and over VL, so K and L recognizable, but not Pressburger, then the theory of putting it again with this predicate, maybe write it twice, but doesn't matter, would be undecidable by our theorem, but by Büchi's theorem, the theory has to be decidable. So it's Cobham-Semenov follows very, very easily out of this undecidability result from known results from Büchi. Okay, let me explain. So this is not comes really not out of nowhere. There have been several earlier results. So if you take K and L multiplicity independent, K and L will always be multiplicity independent. So maybe I shouldn't say this every time. If you take the Pressburger expanded by all K recognizable sets and by all L recognizable sets, then the theory is known by Wilhelm to be undecidable. Dash in 96 proved that, really non-trivially, that it's enough to, if you have all K recognizable sets, then it's enough to have one L recognizable set that is not Pressburger definable. So really to point this out, I will come back to this, in both cases, so this is really the, in both cases, multiplication is definable. And undecidability really comes immediately from Gödel's theorem. So really the picture is as follows. You have Pressburger in the middle tame. You have this Y on the one side, and together with all of VK, you get undecidability, but you really want to get it down the length to 1x on the other side. Okay, I derive this. This is now the result again that I want to prove. So this is that if you have two sets, xk recognizable, ly L recognizable, not Pressburger, then it's undecidable. Crucially, we use a lemma in Besch's paper, and this really says if you have any set, any K recognizable set, you have any K recognizable set, that is not Pressburger, then you already know that the Pressburger with this set defines K to the n. This really boils all this down, all this result on the top, to a very, a priori, very simple question. All what you have to show is that for K and L, multiplicity independent, you have to show that the theory of the natural numbers with so Pressburger with K to the n and L to the n is undecidable. Then you get this strong coupling. And this is really, for me, this was the original motivation of this whole thing, because here you see, you know that with K to the n, it's decidable. So a little bit of multiplication you can add. But if you add a second really independent multiplication, you get undecidable. This itself was an open question raised in the early 80s. In some sense, what do I say next? It's kind of unfortunate that this is not true. It's one of the decidability results where you would really like it to be true. For example, to give you one example of a true statement that is coded in this theory, and which is a corollary of Baker's Fields medal winning theorem on linear forms, which says that for every, so it basically says that if you have powers of 2 and powers of 3, eventually they will grow apart. So for every fixed distance m, you can find a constant c, such that for if we have n1 and n2 are bigger than c, then 2 to the n minus 1 and r to the n minus 2 to r to the n2 have to be at least m apart. And this is, you can easily check, and I think I give this here through the contraposit, I think, is the expressible in a first order statement here. So this is a hard mathematical theorem, and it would be nice to actually be able. So what does it mean? I mean, there's for us logicians, there's always this kind of view. If you take this expansion and you want to check could it be decidable or not, if there are statements in the theory that you could decide that with a Fields medal, then the theory is almost always undecidable. Okay, so this is the. So now I want to talk a little bit about the proof. I do this for simplicity. I do it for the kind of the easiest numbers 2 and 3. So I consider this expansion. I define two things. I will just be very brief. I will be technical, and then I will stop go back to kind of telling the story. So lambda is a function that maps 2 to any element x to the nearest power of 2. It's a floor function, but on the powers of 2. That's what it is. The more complicated function that we need, and this is really the key part, is this s to the y. And really what this is s, if you take y a power of 2, then this takes as a subset of the powers of 3. Note that every power of 3 has a binary, you can write as in a binary expansion, and you want in this to take all the powers of 3 where y appears as the second largest power. So not as the first largest power in the binary representation, but at the second largest power. For example, you could have a power of 3 that is rather close or rather far away to a power of 2, and depending on it, you know where the second largest power lies. So if they're very, very close together, the power of 3 and power of 2, and the second digit will be very, very small. But you have lots and lots of freedom in how the binary representations of powers and 3 and lie. Just to give you an example to explain what this is. So for example, if you take 8, that's 2 to the 3, then 27 is in this S8, because 27 is 16 plus 8 plus 2 plus 1, and 8 is the second largest power of 2 that appears in the binary representation. And these things, and this is the line above all of this, this set is definable and not even so hard to define it in this set, and this is just too complicated. You can prove actually finite, and you can show that for every y and 2 to the n, sy is finite. This follows actually out of Baker's theorem, but there's no uniform bound on the size of or even of the cardinality of these kind of sets. And this is just too generic. Okay, I will state the main lemma, and this may be kind of one of the big differences in this decidability result to the other decidability results that came beforehand is that it does not define multiplication. So many of these results of a Pressburger, if you show that an expansion of Pressburger is decidable, you show that multiplication is outright definable. That's the traditional. In this case, that we'll actually point this out in a second, multiplication will not be definable, so you have to do it other way. What we actually show is that a certain undecidable second-order theory, monadic second-order theory, is actually expressible in this. And the thing that you can do, I just state this main lemma, is basically that this S function allows you to code arbitrary sets of the grid. So for example, if you, so what this says, you have 1 to the n is a natural number. You take any partition of it, and then you can find an S in, so power of, basically this represents a power of 2, such that between two certain powers of 3, you will find this consecutive powers of 2 code all this partition. So really what we can do is we can find this 2 to the s, this powers of 3, and we can make sure that for every kind of pattern you draw into this grid, we'll find a power of 2 that is a power of 2 to the s and a power of these two powers of 3 that satisfy this. So this will allow us, or that what this allows us is that this, here's it. This allows us to allow to arbitrary large finite subsets of n squared, and hence we can encode the weak monadic second-order theory of the grid, and this the weak monadic second-order theory of the grid. So of n squared with the two possible successor function is known to be undecidable. Yeah. So in this proof really just depends on the density of the main lemma. So as I said, in particular, particularly we do not define multiplication. We really just kind of find this, can interpret this second order theory in this kind of binary representation of powers of 3. Okay, I don't want to go more into the proof. I think this of the dilemma, that is too technical. But I want to answer now for the last so many minutes I have. I want to answer these kind of questions. Okay, what if you play with little bit with the structure? So the first thing I wanted to say, so it's very dark, right? Okay, so yes, okay, so I kind of tried to convince you that you should believe me that this theory is not decidable, but I also want to give you at least the idea why it does not define multiplication. This is due to Christian Schulz. He did this, so Chris Schulz, he did it for as in his PhD with me in Urbana, and the idea is as follows. I have to define two notions of smallness and largeness for subsets of the integers or natural numbers. Doesn't matter. So zero natural density is if this lim sup is zero. So if the set is very sparse, it's very large. So this kind of largeness and smallness if it's piecewise syndetic. So this is saying piecewise syndetic is if there is a B such that there are arbitrary long intervals where the gaps in X are bounded by B. So if it's not, the gaps are not bounded by B in general, but on large enough pieces of the natural numbers, these gaps are small. So that this kind of thing is about our largeness. And what Christian showed is that if you take a take a subset of the integers, natural numbers 1, of course, 2, such that if you map it, any power of it, under a Pressburger definable map, then it stays small. So it has zero natural density. So then and what he showed is that if that is true, then it's true for every subset definable from E, and not only from E, but you can add this kind of hashtag to it that says that this is the expansion not by E, but also by every subset of every power of E. So in particular, any subset of E is also in there. So this somehow shows that if you start with something small, then all definable sets are either small or large in the sense of piecewise synthetic. So if you want to, for example, this is true, if you take the powers of 2 and powers of 3, that's really just a statement more or less in number theory. So if E is a union of 2 and 3, then under it's basically linear maps, the image of E to the n has still zero natural density, so is small. So the only thing now to show that the expansion by 2 powers of 2 and powers of 3 is to show that there is an arithmetic set which is neither piecewise synthetic nor does not have zero natural density. And that is, for example, the square free numbers. So if multiplication would be definable, the square free numbers would be definable, but by this result they can't be. So in this structure, powers you cannot possibly define multiplication. All right. So of course you can change this in other ways. One thing I didn't say so explicitly is the kind of if you have the natural numbers with plus, then the order is of course definable. But if you start with Zn plus, then the order is not definable. Can do what it. And so that's of course the question: does the same result hold if you do it just over the integers? So basically, this asks: is the order really necessary? And the answer is very much yes. So Gabe Conan, the model theorist, he showed that this theory is well-behaved model theoretically. So it's combinatorial tame, if you want so. But a student of mine also showed that the theory is decidable if you can decide this much simpler question, which is that if I give you a linear equation with coefficients in Q, then you can compute the set of non-degenerate solutions, so where no subset is zero, in K to the n union L to the n. So it's just, can you solve linear equations in 2 to the n and 3 to the n? To my surprise, this actually wasn't known, but this year, last year, the Kremos, Luca, Neuwitz, Okani, and Vorel, they sat down and actually, oh yeah, of course, in this special case, we can do it. And they showed that such solutions are computable. And they deduced from that, first of all, it follows from that, of course, that the theory with the integers and so without order is decidable. But they also showed that this means that the existential theory, even with order, remains decidable. So, and they looked at our proof of Schulze and myself, and they observed that really what we've shown is that the EAE fragment is already undecidable. Remember that the statement that I gave you, this Fields metal winning statement, that was actually an EA statement. So that could still be decidable, that we really do not know. What I point out, so I think the question was at the beginning of what would happen if one doesn't have equality. I've never really thought about this, but I would guess that is fine. Semenov in the 80s showed that if you forget about addition, then you have to explicitly add order, then the theory is decidable. Recently also, I mean, I think the original somehow sparked some interest again in these kind of questions, it was also shown that the monadic second order theory of this struct theory, this is surely false if you add an addition, it remains decidable, at least. I have one more slide. I had this at the beginning. I mean, for me, there are these kind of questions about how much addition you can add while staying decidable is also very, very natural over the reals. There, kind of, you can add multiplication even in, let's say, without the powers and stay decidable. So you also have a little bit more room to kind of extend it. The proof that Chris and I gave for the naturals works exactly the same way over the reals. There's really kind of no need to do it over the naturals. And in this case, you also do not define multiplication. Here, this doesn't follow directly from Büchi's result. Van den Dries in the 80s showed that this theory, if you add multiplication in the power of 2, is decidable if, of course, k is computable itself. Because you now can take real numbers instead of just natural numbers. I showed a bit later that if you have multiplication and you have two different powers, you're undecidable. In this case, you define the integers, and because you have multiplication, you're clearly undecidable. So there's no need for this kind of tricks that we do in this case. If there you can ask the same questions, thanks to the now unconditional result to Karimov and now, my student Ian Blanchard, he showed that the existential theory also in this case is also decidable. But any kind of larger fragment, we do not know. Yes, please.
Isn't quality defined the plus the level of minus? So if you have minus, in order to prove that A and B are correct, A minus B plus C arbitrary C, you have to C.
Oh, I see. So if you do A plus and minus, then you would get A. Yes, that would be my worry. I mean, what would be your atomic formulas in this case if you don't have equality?
Yeah, but if you have the graph of plus instead of
you would have the graph of
relation, yeah.
I see. Yeah, then.
Yeah.
Exactly, yeah. Oh, I see. Then you're right.
And then, yeah.
Then you're okay. So I leave as an open question, which I like quite a bit. As the last thing I said is the existential. So we know that the existential theory of plus is decidable. With multiplication, we do not. This I find really interesting. Maybe may not look like this, but it encodes essentially quite a lot about the Diophantine approximation of the K-logarithm of L. And you really have to know how semi-algebraic functions or polynomials approximate this logarithm, and that we simply do not know. Okay, yeah, that is it. Thank you very much.
So guys, comments, questions.